If you have a Bally or Stern early solid state pinball machine, in this video I can show you how to make this simple circuit board under 20 bucks, including an Arduino, and you can plug that into your Bally or Stern pinball machine so you can write new rules for it, you can add sound to it, add modes, wizard modes, all that kind of stuff. So a game like Stern Stars can go from something like this, where you basically, just want to have one goal of lighting all 5 stars and going through the spinner, to something like this, where your stars have multiple levels, you have modes, you have a wizard mode, all that fun stuff that was not really thought of in the late 70s pinball machines. This year I bought and fixed up some early solid state machines. We're talking really early. I've got Blackjack from 77 and Stars from 78. And these machines came right after the electromechanical machines, so you don't get much flashing lights. The only sounds you get are chimes, and you get a very, very shallow rule set. They're great layouts and they're fun to play, but there's not a whole lot of depth to them. So for instance, I have Blackjack, and once you get your hand better than the dealer's hand, you're pretty much just trying to hit that saucer, because every time you hit the saucer, you get points, and you get your bonus multiplier. So get the hand right, just hit the saucer, saucer, saucer. That's all you're doing. I thought it'd be interesting in Blackjack if the game actually dealt you a hand of cards that you could see on the display, and then you had to hit to add to your hand, or you had to surrender your bet. You're actually wagering your bonus in the new tool set. And then for stars, you're just trying to light the 5 stars and then hit the spinner, because if you light all 5 stars, that's 1,000 per spin. So you're just trying to hit the spinner over and over again. So again, not a whole lot of depth there. I wanted to add a goal for the stars, where you have to collect 3 levels of stars, a goal for the drop targets, a goal for the pop bumpers, and then if you get all 3 of those goals done, then you get into a wizard mode. So that's what I wanted, but I wasn't sure exactly how to get there. When I was fixing the processor boards, this is a processor for these machines, a processor MPU board for these machines. I started looking at this connector up top here. It's called J5. It was like listed as a diagnostics port, I guess. I think there was a little card you could plug in there to see if what parts of your board were having failures. And the interesting thing about J5 is it has all the data lines, it has all the address lines, it has almost all of the control signals, and it has power and ground. This is essentially, can do everything that the 6800, the ROMs, and the RAM do on this board. So anyway, I figured, what if I could plug the Arduino into J5 on this board, take control of it, and then control the pinball machine. And so I started to figure, if I had that idea, then somebody else must have had that idea too, because I'm new to this, but these machines have been around for 40 years, and there's tons of people working on this kind of stuff. So I started looking around, and I found that there are plenty of Arduino controllers, mostly like with the Mega or something else, Arduino, for pinball machines, and they're built as like replacement boards for that MPU that I just showed you. And there's also other architectures. There's one built on, I think it's called Lee C35, that's built on maybe a Raspberry Pi. I could be getting this wrong. And then there's Altec boards and Weebly boards. There's boards built on different things where you could program your own games. But they didn't do exactly what I wanted, because what I wanted to do was plug something into the pinball machine that would reprogram it, but I could just pop it right off. So if I went to sell the machine, I didn't want to have to sell it with a replacement board that costs like 200 bucks or whatever. You pop it on J5, it takes control and does what it needs to do, and then if you want to sell the machine later or whatever, you pop off your J5, and that was the dream. I wasn't sure if it was possible or not. So on a side note, when I was researching Arduinos and pinball machines, I found the best flame war from 5 years ago. And there's a guy, and he totally inspired me, because he wasn't just skeptical of the idea that the Arduino could be a pinball controller. He was super mad about the idea that anybody would think that the Arduino could, operate in this capacity. And his objections were really interesting because he was saying how you would miss switch hits and you wouldn't be able to turn on the lights in time, and it's not a real-time operating system and all this other kind of stuff. The Arduino is just a chip that you program. It just runs whatever program you put on it. So if you're programming for something to completely replace the MPU, you have to realize that switches are read here on the 120 hertz interrupt. So you can't miss a switch hit if you are checking all the switches every 120 hertz on an interrupt, and you always service that. Same with the lamps. Same with the solenoids. All that stuff is done in an interrupt service routine that's triggered either by the 555 timer for the displays, or by the 120 hertz interrupt that's generated by the power supply itself. So I didn't understand the objections, but I love that kind of thing where somebody is, not just, they don't just have doubts about what you're trying to do, but they seem angry at you for trying. Building this board to interface with the solid state machines is actually really easy. First thing you need is the Arduino Nano. This is a knockoff by Elegoo. It's based on the 18 mega 328p. It uses the CH340 drivers. You'll have to go into the Arduino settings in the IDE and say, old bootloader. That kind of thing is documented everywhere. But anyway, the reason I mention is because Arduino has replaced the Nano with the Arduino Nano Every, and they've changed the way that the pins are accessed in the Arduino Nano Every. So the software as written is not going to work with it. I have to do direct pin access to get the speed I need to read and write to the pins. Anyway, so you'll get the 18 mega 328p version of the Arduino Nano. And you can pick that up for like $5, and it's by far the most expensive part of this board that you're going to buy. I've seen them as cheap as $3, but the price goes up and down with tariffs and stuff. So once you get that board, you're going to put together a circuit board, and there's a couple ways you can go about this. The first ones that I did were just hand wired on, a hobbyist board. And that's pretty easy. It doesn't take more than a couple hours if you're decent at cutting wires and soldering. There's not that many connections, as you can see here from the circuit diagram. Basically, we're just going to plug in the Nano into the J5 connector of the MPU. So let me go through the connections. Oh, before I do that, I said there's a couple ways to do it. One is to wire up your own board. The second is to if you're good with Easy EDA, or if you don't mind designing circuits, you can get a board of your own for probably 10 of them for $5. The third way is there's a guy on Pinside. His name is Roy G. Bev, and he had a board designed, and he was going to do a run of them. So you might reach out to him and see if he's got any of those, or if you could get involved in him doing a run of them. And that way, all you have to do is solder components in. You wouldn't have to do any of this wiring that I'm talking about. But let me go over the wiring, just to kind of document what it does and why it's there. So we're going to work our way from right to left on the J5 connector. I think that makes most sense. The first 8 pins are just the data pins, and they're just hooked directly into pins D5 through D12 on the Nano, and that's just so that we can write out data to the PIA chips. So the only chips we're going to talk to on the MPU are the PIA chips. We don't need to, and we can't talk to the RAM and the ROM through this board. And the reason being is we don't have enough address lines to address the RAM and the ROM, and it doesn't make any difference to the programming of this project. So what we do have enough address lines for is to talk to the PIA chips, because the PIA chips only live at 8 different addresses. They live at, one of them, U10, lives at 88 through 8B, and the other one, U11, lives at 90 through 93, and that's in hex, of course. And then also the last pin we have available on the Nano I've put towards talking to the SB100, which is the soundboard that Stern introduced, I think, in '79. Because I was programming for Stearns Trident, and I wanted to talk to the soundboard, and it just needed one more pin because the soundboard lives at address A0, so that just needed one more pin from what I'm doing. So let's look at the address lines here. You'll see that some of these address lines are in green, and the reason being is that those address lines are actually controlled through the 74-125. So the purple lines are hooked directly into the Nano, and they are going to dial in the addresses for the PIA chips. As I mentioned, like if we want to dial in 88, we're going to just turn on two of these lines. However, the chip select for the PIA chips has to be require that A9 and A12 are low when we're trying to talk to them in this way. So to drag A9 and A12 low, we have to drag pins 13 and 10 low on the J5 connector, and I'm doing that through this line buffer here. And the reason being is that when you flip a switch and you want to boot into the Arduino code, the 74-125 is triggered with this switch here. So normally it's pulled up to 10K, but then you ground it when you want to boot to the Arduino. And when you ground that, it's going to put ground on 4Y and 3Y here. I think, I'm wrong about that. Looks like 3Y and 2Y. So that it'll drag the chip select, so when the Nano is booting, we're only talking to the PIA chips. However, if you want to boot to the original processor and you leave that switch up, then your G lines, will, on the 74-125 will be dragged high by the pull-up resistor to 10, the 10K pull-up resistor, and therefore those lines will be tri-stated, so the 74-125 won't interfere with what the 6800 is trying to do. So if you can think of it this way, any green lines you see are going to be grounded when the Arduino is on, and that's so that we can do the chip select for the PIA chips. And you'll see that there's also a green line over here onto 24. That's the halt line for the processor. So it's actually, if you raise, it's actually halt complement. So by pulling 24 low, we're stopping the M6800 processor, and we're only running Arduino software. So that's the address lines. The one funny one here is 17. I kind of glossed over. 17 is the one I need to talk to the SB100, and that's eventually plugged into D13 of the Arduino. The one thing about the Arduino Nano, or at least this one, is that D13 is, I think, pulled high by the LED. There's a little onboard LED here. So we have to buffer that line too, or else D13 will trip up the 6800 if you want to boot to the 6800. Anyway, so I ran that through the 74-125. I had an extra tri-statable line buffer there, so I just ran it through that. And that's the reason for the 74-125 on this board, and that's the reason for the 10K resistor. Obviously, the only other component here is the Nano. So then there's just a couple other control lines that we hook up to the Nano, read-write on pin 23, and VMA, valid memory address, the clock signal, and then we pull power and ground. So this board, is kind of parasitic on the power and ground coming off at J5. And that allows us to do all the proper control signals to talk to the PIA chips also. You have to, get the chip enables just right and all that stuff. There's one more pin, and the reason why these last two are in parentheses is that depending on what MPU you have, what board you're running, like the 35 will have 34 pins on it. The AS2518-35 has 34 pins on it. And the last pin is the interrupt pin. We also need the interrupt pin because we need to be able to tell when the 120 hertz interrupt is coming and when the display interrupt, which is about 320 hertz, is coming, so that we can do the timing properly. And you can pull that from the -35 board right off of pin 34. If you have an older board like the -17 or the MPU 100, you only have 32 pins on J5. So therefore, you'll see on the boards, at least the ones that I'm running to the old style, there'll be a little jumper hanging off of here on the corner. And this is a little alligator clip that I clipped to the top lead of R134 on the MPU board. So that's the board. You can build it. You could design your own, or you could buy it from, like I said, I think Roy G. Bev on Pinside is doing an order of these boards, or he has already done an order of these boards, depending on when you're watching this. So you may be able to grab one from him. So after I developed the Arduino board to plug the Arduino into the pinball machines, and I wrote some basic test software to make sure that it was all working, I decided I needed a library. I needed a library of functions so that I could talk to the pinball machine in a consistent way across all my game implementations. So I created this library called the Bally Operating System, and I've shortened that to BSOS. It has functions for the lamps, displays, switches, solenoids, and sounds. There are a couple of utility functions. There's a setup function that attaches the interrupt service routine to the interrupt line coming from the board. And that allows it to sync with the zero crossing interrupt the same way as the old code did. And it also gets the 320 hertz interrupt so that it can do the display's digit display. There's a setup function where you can pass it in a short list of game switches that control immediate solenoids, and this is for things like pop bumpers or slingshots, things that need to fire as soon as they see a switch hit. And then there's another setup function to get the dip switches. So then I have a few functions that deal with the switches specifically. As I said, they're read in the zero crossing interrupt service routine, just like the old code. And as soon as I read a valid closure, which is open, close, closed, it's just software debouncing method that the old code used. I take that switch hit and I store it in a first in, first out stack so that your game code can never miss a switch hit. You can just have a little loop in your program control where you read all the switches and act appropriately. There were situations in the early Stern and Bally machines where they would do sound callouts on the chimes, and while that sound callout was running, it was just basically sitting in a little intensive loop, counting off a certain amount of time and then doing a chime, counting off the time and doing a chime, and it would catch one switch hit during that time, but if you had a second switch hit or a third switch hit during that sound callout, it wasn't going to catch it, and so my code stores all your switches to that first in, first out stack so that you'll never miss it. You can service that whenever you get to it, but if you have something that's going to be intensive, your interrupt service routine is still going to manage to pick up your switch hits and you're not going to drop any. For the solenoids, there's some functions to control the continuous solenoids, and that's for things like flippers and the coin lockout. Then there's also a first in, first out stack where you can say, hey, I want to fire off a solenoid, for instance, to clear the drop targets or play a chime, something like that, or kick the ball from the out hole into the shooter lane. And then I also give a time stack. And the reason why I implemented the time stack was because some of these games have chimes in them. It's a lot easier to just say, okay, we're at time X, and then at time X plus 1500 milliseconds, I want to play this chime. And so you can push all of your chime calls to the stack at once and just know that they will update at whatever point in the future when we get to it. For the displays, there's a couple of convenience functions to just set the whole display by magnitude, and that's really useful for scores and stuff. Because on these displays, you can control each digit, whether or not it's blank or it's got a digit in it. Using that, you can do some special effects with the displays. I like to have displays that kind of have a rolling blank go through them when the machine is idle, and that was introduced in later machines. I think it helps. If a player is, got the ball cradled on a flipper and they look up, it's going to draw their eye to their scores. I like effects like that with the scores. I also like the early games did not have the concept of flashing the score before the playfield was validated. So I like to do that too. So I've got functions in there to do, flashing scores, rolling blanks, all that kind of stuff. For the lamps, it's pretty simple. I've got a function that allows you to set the state of each lamp individually, but then you can set the state to on or off. You can give it a dim level, or you can say if it's flashing. For sound, I've only implemented the SB100 and the Squawk and Talk so far. When I build a board, I'll mirror the J5 connection on the top of my board, so you can still plug the SB100 in. For the Squawk and Talk, that is a Bally thing, and that goes right through the solenoid control. There's a little weird timing thing it does where it writes it out almost as if it's a solenoid. So you can do that through the Squawk and Talk function that I've got in the library. So that's pretty much it for the code. So that's the project. It's cheap. You can build your own board for 20 bucks or less. I don't sell anything, but I offer all the plans for free, as well as the software. The software is all free. There'll be a link to GitHub below so that you can grab all the software and check out what I've done. There's even more in-depth documentation on my website. I'll put a link to that below as well. There's a peripheral interface on the boards that I build, and that allows me to hook up. You may have noticed the fancy digital sounds of music on stars. That uses a wave trigger and speakers, and that increases the cost of the project quite a bit, but I think it's worth it. So far, I've written Stars, Blackjack, Matahari, and Trident. I've got more games coming soon. I hope you give it a shot. If you've got one of those games, or if you've got your own game that you want to try to rewrite, process is pretty simple, and I think with all the examples I have out there on GitHub, you should be able to figure out, how to make the game do exactly what you want. So I hope you give it a shot. It's just a fun hobby for me, and I hope you enjoy it. Thanks for watching.